Here's another Coulomb's law problem. Looks a little bit different though. Let's read through it and see how it looks different than the last question we dealt with. It says a small metal sphere with a negative charge, call it charge 1, negative charge 2.1 times 10 to the negative 6 coulombs, is to the left of another one, sphere B or sphere 2, whatever you want to call it, 1.5 times 10 to the minus 6 coulombs. Oops, that's not what we want. 1.5 times 10 to the negative 6 coulombs, a distance of 2 times 10 to the negative 2 meters. All right, so far so good, right? This doesn't look any different than anything we've done so far. Got a third sphere, sphere C, that has a positive charge of 1.8 that's situated, situated below sphere 2. This guy is down here. 1.8 times 10 to the negative 6, positive. 3 times 10 to the negative 2 meters. Uh-oh. I don't think I like this. What's the same about this question? Not the question we just did, right? The crazy one where the forces had to balance. But that general question where 3 were in a row, what's the same about it? We have 3 objects. There's 2 forces acting on sphere 2. The force of 1 on 2, the force of 3 on 2, right? That would be the same as if they were all in a straight line, right? Hey, what's different about it? We got to be asking ourselves this question pretty much every question we see now, ever since we did momentum. We got 2 dimensions here, right? Let's draw a free body diagram just like we did in these problems. We're going to see that free body diagram gives us 2 dimensions. 2 is pulled towards number 1. It's attracted to number 1. 2 is pushed away from number 3. Pushed up, away from it. And we can find these forces, right? F21, F32, that's pretty easy to find. We got our numbers here, 8.99 times 10 to the 9, that's that big constant. Q1, we drop the sign of the charge there, right? We always do that. Q2 is not a big fan of dealing with exponents like that. It just makes it a little bit more cumbersome on our calculator, but it's not that bad, right? R is 2 times 10 to the negative 2. We do that, we get 70.8. Let's go a few decimal places there, Zach. Yeah, 70.796. Okay, 25, thank you. Thank you, Zach. 70.79625 Newton. Everybody else get that too? Yeah, good. All right, let's find F31. Or sorry, F32, I should say. Oh, this shouldn't be F21, right? This should have been F12. That's not a huge deal, right? It's the same value. That probably wouldn't have caused us to make a mistake in this, but we'll fix it just to be sure. F32, it's going to be, what, 8.99 times 10 to the 9 times 3, what's that, 1.8 times 10 to the negative 6 times 1.5 times 10 to the negative 6 over 3 times 10 to the negative 2. Thank you, Zach. That one worked out to be 26.97 newtons. Hey, guys, remember what we said back in those 2-dimensional collisions, those T-bone collisions, or those funny angle collisions or explosions. Got to add these vectors together, right? But 26 plus 70 is not 96 here. How do you add them? If 26 plus 70 is not 96, how do we get whatever they are? I heard a little Greek there. Pythagorean theorem. I know, it's hard, right? It's all Greek to me. The Pythagorean theorem we got to do. We know enough Greek, though, to do this, right? We got 70 to the left. We got 26.97. We solve for this. We can do that. We did this enough in momentum to solve for F, right? And then theta drawn at the beginning there. We can solve that as well. Right? What is this? Forget about physics 30 for a second. I mean, this is similar to conservation of momentum in physics 30, right? We didn't have to do as much here. Okay, we got our forces, and then we went straight to the right angle triangle. What is this similar to what we did in physics 20? What's this like? Guy walks 70 meters to the west, then he walks 26 meters to the north. What's his displacement? It's the same question, isn't it? Airplane flies 70.7 meters per second to the west, but there's a wind of 26 meters per second to the north. What's the plane's velocity relative to the ground? It's the same question. Okay. Don't make it harder than it has to be. Good. Let's take a look at two questions on page 534. Remember, as you're doing these, think about whether it's one-dimensional or two-dimensional. If it's two-dimensional, don't get the forces and then just add them up like you would scalars. Okay. Do the right-angled triangle thing. Do the Pythagorean theorem like you do with every other vector, like you always do with every other vector. Think about the red pen, okay, for each of these questions. Think about what you know. Okay, don't forget to draw your free body diagram. All those little things, okay? All right, let's get at it.